A few moments later.
Uh-oh.
Hello guys, Assalamualaikum warahmatullahi wabarakatuh and a very good day. So today we're going to revise back the Dunn method, differentiation method step by step. A lot of people doesn't agree with some video, it needs some clarification. Again, I don't know how many times, so based on other comments, so I consider to do the video step by step. So let's revise and do real time how we plot at the Excel and how we put into the origin for the Dunn method. So the first step is you should understand by doing the Dunn method. Usually we can differentiate between capacitive current or some people call it diffusion limiting or diffusion control current. Okay, so for the cyclic photometry, if you want to apply for the Dunn method, it should process for redox peaks. And the main equation that we're going to implement is the current at the fixed voltage equal to the constant K1 times the scan rate and also the constant times scan rate power half, whereby the yellow color, whereby your constant times scan rate is your capacitive current and your green color constant times scan rate power half is your diffusion control current. And when you apply, you divide by scan rate power half, whereby you got y equal to mx plus c. So your y equal to your current at fixed voltage, divided by scan rate power half equal to mx. Your gradient is your k1 and your C is your K2. By plotting a straight line, you can get the value of K1 and also the value of K2. Okay, so that's the very basic. So I'm apologize for the noise. So I'm at my hometown. So some a little bit motorcycle sound. I think it's okay for you, right? Okay, for next, you should have the cyclic photometry at different scan rate. So it's important. Minimum is 3, maximum is can be a lot of scan rate. So the best if you can have the scan rate preferable at lower scan rate, because if your gap between scan rate is big, the graph might not be very nice. So it depends. The value also will be depends on your scan rate gaps. Okay, so I think this all is understand. Okay, then you fix a voltage. So fix a voltage is important. In this case, I fix at 0.35 volt. You can go to 0.4 or 0.5, whatever voltage around your potential window. But I'm not encourage you to take the here the cathodic one, better take the anodic one. So the value might be different a little bit if you take at anodic and also cathodic. So it's also a choice and a variables. It's not a constant variables. You can fix. You need to fix either one. Okay, so go to the procedure. So how to get this procedure? So a lot of people know that to get this procedure, you just need to plot the current at fixed voltage, divided by square root power half. We're going to plot and get this type of graph. So how we going to get that? So this is just a briefing. Later we'll do step by step. Don't worry. And by having that, you use the origin, go to analysis, fitting, and fit linear. You got a nice slope and also the y-intercept. Some might curious, might answer why is negative, how to do that, and so on. So you can get from here is the slope is the k1 and k2 is the y-intercept. Okay. So from that you can calculate the contribution, and after that what you can do is you can get this nice graph. From here, by the theoretical is said that the area close to the zero is the capacitive area and the area away from the zero is diffusion area. So by the theory, we separate like that, so you know where is your capacitive and diffusion, and then you calculate the value of current at each graph, and after that you can get your contribution current. So it's quite straightforward. Then the v value and r square, a lot of people know already how to plot, so let me show you how to plot it one by one. Okay, let's start the discussion with the Tapo pula orang kata. Okay, let's start the discussion with the first graph. We need a cyclic voltammetry at different scan rate. So I already opened you the origin. So let's fix the voltage at which voltage you're going to pick. So just click a line here. So after you click a line, then draw a line. For example, here I draw at 0.4. So make sure the line is almost straight as possible. Okay, then what you need to do, click here. We got the data reader. Yeah, we got here the annotation. Let's click here and read the first one. This box, click here. Okay, what you need to do, you read. So you need to read at this line at 1 millivolt per second. So the important thing is just read the current density. So just read the current density. Here is the y-axis is important for you. So y-axis 1.82 ampere per gram. So 1.82. So around that. So you're going to open your Excel and put the value of your current. Okay, this is the example, the existing that I already have. So what you need to do, if you're going to focus on this graph, you need to make another column, current at 0.4 volt, and click here, read the value, and just put the value. Okay, like here, the red color is around 2.45. So 2.45. So and the rest of the graph. So that's how you're going to read the current density. So when you read the current density, so you just make Excel like this one, scan rate, your fixed current, and the value, your fixed voltage, and also the value of your current. So you can use the just current or current density. Just make sure you fix the value. Don't change in the middle or whatever. Okay. So here. Then after that, you can go for the log scan rate and also for the log current. So it's important. And from this graph, if you already have this graph, then you can go to the B value. Okay, because V value, we obtain the V value by having the log current versus log scan rate. So you got the V value. So the V value exists when you got this Excel. So we need the log scan rate and log current, then you can get the V value. So let me show you how to get the V value. So first of all, let's say I have already log scan rate and log current. So I just plot using the scattered. So then, oh my god, so it's locked due to many windows. So I cannot replot it. So it's okay. So I can just copy first. So click to the V value. So okay, I just click copy and make another one. Still cannot because too much window. It's okay, I just show you how to do it. Okay, let's say this is graph how I get the straight line. You go to the analysis and go to the mathematics. So from here, you go to the analysis and go to the fitting. So fitting, you go to linear fit. Just click the linear fit. So when you click the linear fit, then you will get the value. They will give you the value. So in this case, they will show like this one, and you just click OK. So after you click OK, they sum up for you y equal to mx plus c. So here they said that your intercept is around negative 2.67. Your slope is 0.34. So your b value is 0.34. It's like that. So that's how you get the b value. Okay, so next we're going to see the R square. R square we're not sure. A lot of people already know. Just plot the square root over square root power half, then you can get the R square. So the R square, the graph is looks like this one. Yeah, it looks like this one. So current over square root power half, you can get the R square. So the most important thing that a lot of people argue is about the K value. So to get the K value, you need to fix the potential at 0.4 volt. So how you fix the potential? First, you need to have CV at different square rate. So CV at different square rate, like this one, I have square rate 1 to 10, but I just use until 5 only. So you need to have a square rate CV cyclic voltammetry at different square rate, and you need to fix the voltage. It can be 0.4, it can be 0.35, and so on. So after that, go to your Excel, read the current, oxidation current, and also reduction current. So read the oxidation current and reduction current. How to read the oxidation current and reduction current? Okay, for example, here I figured at 0.4. So just click here the data reader. So so what you need to do, just click at the data reader here, the annotation, then oxidation current is here. 1, 2, 3, 4, 5, 6, and above. That is the oxidation current. You need to get the value at this value. How much is it? You need to get the value here. At the box, you can see the value of Y is 1.84 and so on. And then for the reduction current is below here. Here, below. Let's say you want to do the red color, the below. So do for all scan rate. You need to do for all scan rate. So when you do for all scan rate, you got the oxidation current and reduction current. Let's say you do until 5 scan rate. It's okay. Okay, for scan rate power of half, what you can do, you just use the formula equal power and your scan rate. Let's say in this is D2, comma 0.5. So power of 0.5. So then click enter. So you will get on for the rest. Scan rate I use for millivolt per second. I use millivolt per second. If you want to use volt per second, also can. Okay, depends on you. Okay, because I use millivolt per second, because I fix it for millivolt per second. If you want to use volt per second, also can. Okay, then for the oxidation current, this is oxidation current divided by scan rate power half. So what you can do, you can equal to B2. B2 is our oxidation current divided by E2 here. E2 is our scan rate power half. So you can get the oxidation current and also reduction current, the scan rate power half. So it's not that difficult. You just include the formula. Okay. For the reduction current and oxidation current, also you got to know. Because why we need to do this one? Because to get the key value, if you understand from let's say we revise back the chapter, to get the key value, we need to get, I think here, yeah, this one. We need to plot the current at fixed voltage divided by square root power half. That is your y, and your x is square root power half. So you need the value of current divided by square root power half as your y-axis, and your axis need to be square root power half. So here we have our current in this case, why I choose oxidation and reduction, actually you can choose either one because this is the backup plan. So actually for in this case I use for the oxidation current. So for oxidation current here, become my y-axis and my x-axis is square root power half. So here you take these two and plot in the origin. So when you plot into the origin, so I got the k value here. So the k value, so I double click here. This is my k value. So from here, the same thing, you go to the analysis and go to the fitting and click linear fit. After you click the linear fit, this equation will come up and will show you that your intercept is how much and your slope is how much. So your slope is from 5 point something and intercept equal to negative something. Okay, so why I get 2k value? Because this one is negative. Then I try another one to see if I got the positive value. So in this case, the intercept I got is positive, but the slope is negative. So it can be either one. Because in this case, to make it easy, if either one is negative, just ignore the negative, make it the epsilons. So then from here, you already get your K1 and also K2 from the slope and from the intercept. So I think everyone from here can get the K1 and K2 value. The hardest part is how you want to get this one. Some might misinterpret or a little bit difficult to plot this one. Okay, so you already come to the hardest part to get how to get the K1 and also K2. So what you need, open your Excel and here. So you open your Excel, click the contribution, make a tab called contribution. So in this tab, so make a scan rate. So you let in the earlier one, I got 5 scan rate. You got the scan rate. So I just put scan rate power half, my K1 value and K2 value. The value must be fixed throughout the other scan rate. You see, the value is fixed. So then I want to calculate my capacitive and diffusion. How I do that? My capacitive, based on the theory, go back to the theory to get the capacitive, the yellow color, is K1 times your scan rate. So click here, your K1 value is 0.000581 times with your scan rate. Your scan rate is 1, so the value is the same. Okay, that is your capacitive, and the rest follow. This 1 times your scan rate is 2, then the rest is so on. Okay, that's for K1V. And for diffusion, what you need to do is, you need to go back to the slide, you go for diffusion is K2 times square root power half. So K2 times square root power half, K2 value you can get from the graph, times square root power half. Okay, this is your square root power half B. Okay, then I got my diffusion one. Okay, so I can get my diffusion. And to get my percentage of capacitive and percentage of diffusion, what I'm going to do, the formula for percentage capacitive equal to capacitive divided by capacitive plus diffusion times 100. You see here, to get the percentage capacitive, what I'm going to do, E2 is capacitive K1V divided by K1V plus K2V. Okay, times 100. That's how I get the percentage capacitive. And percentage diffusion is the same. However, what you need to do is you need to do diffusion divide by capacitive plus diffusion times 100. So that's how you get it. Okay, so now you got in terms of percentage. So if we already know in terms of percentage, you can plot, if I'm not mistaken, the bar chart, GCD bar, the bar chart. Is it this one? Let me check this one. No, I don't think I plot for the bar chart. So yeah, this one, yeah, contribution. You can plot in terms of bar chart. Let's say in scan rate 1, the contribution of diffusion limiting how much, diffusion how much. So in the bar chart, you can plot. Okay. However, people are wondering and they want to see graph like this one. So how can they achieve this graph? Okay, for to achieve this graph, it's a little bit difficult, not that difficult. So we're going to see here the Dunn real. Okay, just you need another tab called Dunn graph. Okay, so first is the potential. Okay, like in this graph, we just pick 1 millivolt per second. Means that I want to know the contribution at just 1 millivolt per second. If you want to plot for the other scan rate also can, it's no problem. So then what I need to do, I need to divide the potential into sub-segment. So how I divide into sub-segment, so here you see my potential window is from 0 to 0.5. So I'm going to read the current density, current response at each interval, at 0 volt, 0.05 volt, 0.1 volt, 0.2 volt. What is the current response? How to read that? So how to read that? What you need to do, I think I already plot. Let me see, CV line, contribution before, yeah, this one. You need to divide into each 0.05. So make a line into each interval. The smaller the interval, the better. So you can get more accurate one. So then click your data reader and read the value. For your information, at value 0, your y-axis is the same for anodic and cathodic. And at value the maximum of your potential window, also the same. Okay, then you need to read at the rest of the voltage. What is the value of current? So when you read, for example, at 0.4 volt, how much? 0.45, how much? You need to read all. So it's a very tedious if you have a bigger potential window. No shortcut in this term. So then put the value here. The reduction and oxidation means that the current density at reduction, current density at oxidation. So when I read, I put all the value. Like I clarified earlier, the value at 0, the minimum and maximum is the same for oxidation and reduction. Okay, enough with that. I hope you can get that one by doing like this. Okay, then after that, you want to do the percentage capacitive and also percentage deficient. We already get the value here. You see here, when we calculate, we got capacitive at 1 millivolt per second is 35%, deficient is 64%. So then, what you need to do, convert the percentage. You need to divide by 100. So you can get 0.35, 0.65, around like that. So then we're going to see this one, the value is constant throughout the potential window. This one also constant throughout the potential window for percentage capacitive and deficient. And you want to know that the reduction current after the contribution. Okay, the first two is I'm using the capacitive. So using the capacitive percentage, I want to get the reduction current and oxidation current. And these two, I'm using the percentage of diffusion. So how I get this? So let's see the formula. For R after is D2, your percentage capacitive times B2. And then just click here for all the number. And for oxidation after the capacitive contribution is the C2 times D2. And same for here. This one I'm using the diffusion, and this one also for diffusion. So this one is important for you to get. Somebody say the data is not accurate and so on, is manipulated, because your data is my data is different depending on the value, depending on your current value and your capacitive contribution, it will be different. So just imagine. So let's see, if you don't understand, just imagine. For example, your reduction current is 100, oxidation current, let's say the same, 100. So your capacitive may be 50%, diffusion 50%. So R after means that after the 50% capacity contribution, your R after will be 50 because your initial is 100. Let's say in this case, your initial is 0.0662, and after 35% contribution means that 35% of 0.0662 is 0.02345. If you don't really believe, try 0.02345, you times with 35%, then you can get exactly how much the value, or if you don't under if you don't really if you really want to prove it, 35% is 0.023 and the rest is around 65%, almost will be 0.0662 minus 0.02345. So it's like that. So you need to understand a little bit mathematical here. So after you're done with that, then a lot of people are waiting. So you can actually get the Dunn graph like this one. So how you got the Dunn graph like this one? So to get the Dunn graph like this one, so you just need to do is, so copy all the data from your Excel here. So just copy all from potential to O after. So after that, you see here from potential to O after, I copy all. So just plot here. Start with potential. And this one, R after and O after, you are using your capacitive contribution. And you start with potential again, R after and O after this one for your reduction. You follow, no, not reduction, you follow your diffusion percentage. Okay, so then you just plot, you right click and plot, you can get the graph. So let's see, if you don't believe, people always don't believe, we go here, and copy. Let's try copy. Okay, let's try control copy, but because my origin is not the real version, so I'm going to open a new one. So let's open a new origin and see if we can plot or not. Okay, so wait a little bit. Okay, so let's open the origin. Okay, I think the last step, a lot of people doesn't get it, how to get the reduction current after the contribution. Okay, okay, so we just wait. Okay, so now origin already open. Okay, to all the viewer, if you got the full license for origin, you can give me. It's just a trade, right? You help me with the software, I can help you analyze something. A lot of people just message me, email me, plot this, plot this. So I'm not your I'm not the one that can have time to plot for you. You need to learn. I just here to share the knowledge. So here, so when you go here, let's say we go to the potential and reduction current after, and here we go here, or you want to go all the way. Let's try. Okay, then after this you click this one. Okay, then you got like this one. The graph is not nice. Okay, not nice. Okay, what you can do is you just click, you just double click, and you go to line here. Then from straight line you go to the B spline. Okay, we just try first and click apply. Okay, okay, now it's become better. Okay, so to then you need to change the color, from group, from dependent must become independent. So the line, let me show the first line. Oh no, the color, I need the color to be blue. Second is just the reduction current, so it should be the same blue. And not reduction, the contribution for the reduction. And this one using the diffusion, just using green. And the other one also we want to use green. Okay, okay, now it's become better. So then if you want to do the solid line or area under the curve, you can do that. Click enable, click here, become normal. You can click inclusive, if I'm not mistaken. We can retry, don't worry. Okay, this one, follow the first one. sorry, cannot. You need to click dependent first. Don't enable. You click group dependent first. Here, go to the line, enable inclusive. This one also you go. Oh, okay. It's already dependent. Line. Follow the first one. This one also follow the first one. Okay, let's try. Yeah, I think cannot. Edit window. Okay, let me try because yeah, sometimes we forget. No worry, it's not that big deal. So click line. So fill area under the curve, enable. Inclusive. This one. Oh, no, I know, no, I know. Yeah, no, I know it's the mistake. Don't follow. This one can follow. The third one don't follow. This one also don't follow. Okay, the first one, and after here I want to do the patterns from black color go to the blue. Okay, now it's become blue. So now I know that the blue color is the capacitive and the green color is my diffusion. Sorry, yeah, diffusion. So I think yeah, that's all. We just want to make it easy. So it's not a formal. Everyone can follow. I think it's not that fast. So yeah, it's not that fast. So by doing this, you can know how to plot the contribution. So I think that's all. So if you have any question, you can ask. That's all. See you again. Bye bye.